find the gradients. So just partial x, partial y written as a vector. You guys all match? Everyone take a second, take a look at your whiteboards, and check your answers. Mine is written in IJ form, but it can be written in the corner brackets too. So looks like everybody matches. Good. All right. Yeah, good. All right, any questions on that one? So the three-way gradient would just be with an I, a J, and a K, right? So you'd have, wow, that's big. Does that get simplified at all? No, that's it. So you have a really big three-way. Does everyone have a pretty big giant one like that? Why don't I see number 2? Oh, there it is. There it is. Yeah, that looks good. Yep, very nice. Very nice. Good. I can't see this group's number 2. Oh, you guys just wrote your partials. You just didn't write it as a vector. Okay, make sure you. Oh, it's over there. Oh, you guys use double boards. Okay, got it. All right. Good. Very nice. Yep. Good. Yeah, very nice. Okay, so it doesn't look like we have any questions on gradients. Directional derivatives of the following at the given point in the direction of v. What do you have to convert v to? A unit vector, right? Okay, so you convert v to a unit vector, and then you do the dot product of the, so there's my unit vector for the first one. Sorry, I have to raise this up so you can't see the problem. But it's the dot product of the gradient and the unit vector, right? And then you have to plug in the point. So, anyway, I'm just going to look the right way. Okay. So my final answer was -7/√29. I see it here. So that's good. I see it there. Yes, yes. Yes. Yep. Very good. Good. Yes. Yeah, you did. All right. Fantastic. Last one. All right, so same thing. So directional derivative in the direction of the vector 1, 2 at the point pi fourths, for sine 2x cosine y. So find your unit vector, find your gradient, do the dot product of the gradient and the unit vector, plug in the point pi fourths. And I ended up with -√2/5. Very nice. Oh, you guys like kind of cleaned it up. Oh, you could have just stopped there. Look at you rationalizing. All right. Going above and beyond. All right, good. 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 Oh, yeah, wait, oops. You guys lost a root along the way. So you were really close. You just lost a root on the bottom. So something happened there. Okay. Something happened. Okay. Good. We can take a closer look if you want to later on at your number 4 and see what happens with the root. So, you know what it is? It was times 2/√5, and I think you have 2/5. So, okay, not a big deal. Whoops. Oh, I thought I had fixed all of these, and I didn't. I missed this one. We are not on 13.6b. We are on 14.6b. This is not the hard. Why do you think this is the hardest lesson? Oh, it's not hard.
Did you see what the gradient question is?
You got all those. Those are easy. Like you can do this. Applications are not necessarily harder.
I'm worried that it's reading.
You're gonna be fine.
Literally,
You're gonna be fine.
no one asked your
Now, Monday might be a little bit harder. Tuesday might be a little bit harder. Ooh, I have to record a lesson for you guys for Wednesday. I'm out on Wednesday.
We're having a pizza party on
Extrema,
Wednesday.
relative and absolute extrema of surfaces. We're finding maps like hills and valleys in 3D, right? Yes, that's what I already put in the sub notes. Order pizza. Yes, they will order it, pay for it. Should I? You know what? Should I just put "bring it with you" when you come?
Oh yeah.
Okay. So,
Except we don't want the for them.
it.
You never know. To give it to the AP.
Oh,
Just
just calculate. So during my planning, which is third period, I could put instructions: go out, get pizza, come back, serve 2 calories. All right. All right. Today we're doing applications of gradients. It's not a hard lesson. As a matter of fact, it's a fairly short-ish lesson. We should have time today to either work on quizzes or get some homework done. So, anyway, once you guys are ready, let me give 10 more seconds to write down the title. Are we all good? Oh, wait. Good now? All right, everybody's ready? Let us begin. All right, you do not have to write down this page. This is kind of the leading you into how things work page. So I've kind of been hinting that the gradient is special, right? Why is the gradient special? We have the directional derivative. The directional derivative gives us the slope of the graph in any direction, right? So the directional derivative is pretty awesome. So why do we care about the gradient, which is just kind of a part of the directional derivative? Well, this is going to show you why, mathematically, and then we'll kind of think about it a little bit. So it all starts with the cosine of the angle between 2 vectors. Seems weird that that's where we're starting, but that's where we're starting. So we have, I don't know if you guys remember this or not from chapter 12, but cosine theta equal the cosine of the angle between 2 vectors is the dot product of the vectors divided by the product of their magnitudes. Does that ring a bell? Yes. Good. All right. So I'm going to slowly walk you through this. If we rearrange, we get a new formula for dot product, right? Which we did in chapter 12, right? Okay. So u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between the vectors, right? All right, where are we going with this? Well, we know that, I just mentioned here, of course, I told you all this in chapter 12. I don't know how I re-put it, but anyway, of course, which is why if the dot product is 0, it implies that the vectors are perpendicular, because the only way to get a 0 dot product is if your cosine of your angle, if your angle is pi halves or 3 pi halves, I'm just going to force the vectors to be perpendicular, right? Okay, so anyway, so where are we going with this? Well, here's how we link it to what we're doing. We've already established that a directional derivative is the dot product of the gradient and the unit vector in the direction we want, right? Okay, so let's raise this up a little bit. All right, so if the directional derivative is the dot product of the gradient and u, which is this unit vector in whatever direction we're interested in, right? Well, if we rewrite this in dot product form as the magnitude of the gradient times the magnitude of the unit vector times the cosine of the angle between them, we get this formula. Except, what's the magnitude of the unit vector? It's 1, right? So now what we get is that the directional derivative, which is the dot product of the gradient and the unit vector, is equal to the magnitude of the gradient times the cosine of your angle that we're talking about here. So the angle between the gradient and the vector you're interested in. Okay. So anyway, so now we've got this. Why is this special? Well, here's what makes this kind of neat. I want you to think, I'm not going to show you yet. I just want you to think about it. I want you to think about cosine for a minute. The output of cosine. So what is the highest value that cosine can possibly be? 1. And what is the lowest value that cosine can possibly be? Negative 1. Now, if we do an absolute value on cosine, then the lowest it can be is 0, right? Okay, so if we're just talking positives, highest is 1, lowest is 0. We're talking the whole realm, highest is 1, lowest is negative 1. What that means is what the maximum possible value of the directional derivative could possibly be is equal to what? The magnitude of the gradient. Because the highest value that cosine can take on is 1. So if the highest value, and this is positive, right? It's a magnitude. So if the highest value that cosine can possibly take on is 1, then the maximum possible value of the directional derivative is the gradient, which means the gradient gives you the highest possible derivative value in any direction. So if you, yeah, oh, did you have a question? Okay. So anyway, so if you are, let's see, yeah, okay. So anyway, so if you are looking for where some mountain range has the steepest slope, if you have some graph, a 3D graph of a surface, and you're at some spot, and you want to know in which direction the steepest ascent is, it's in the direction of the gradient. You just find the gradient, the direction of the gradient gives you the highest possible slope, which is kind of neat, right? Okay, so if we talk, I'm just going to, okay. So what does this mean? So the maximum value of the directional derivative occurs when cosine is 1, which means the maximum value of the directional derivative, or the steepest slope of a surface at a specific point, is the magnitude of the gradient. What else does this mean? If the steepest slope occurs when cosine is 1, and if theta is the angle between the gradient and vector u, then the steepest slope occurs when this angle is 0, which means the steepest slope is in the direction of the gradient. Now, you can make discussions, like people talk steepest slope and shallowest slope, but there's steepest ascent, steepest descent, and then shallowest. Well, shallowest to me would mean we're 0, right? So to me, shallowest is kind of silly because it's just wherever the slope is 0. But if we're talking about steepest ascent, so that would be where your cosine is 1. Steepest descent, that's where your cosine is negative 1. So your gradient or negative gradient would give you your highest or lowest possible values, direction of steepest ascent or steepest descent. All right, so I summarize it on the next screen. So the direction of maximum increase of f is the gradient. The maximum value of that derivative, that slope, that rate of change, is the magnitude of the gradient. So the direction of the gradient gives you the direction of steepest ascent. The actual slope itself is the magnitude of the gradient. And then the direction of minimum increase, the negative of the gradient, and the minimum value would be the negative of the magnitude of the negative magnitude of the gradient. I learned that, so our old book, I don't know, I haven't looked in the new book. Our old book didn't teach why the gradient gave the steepest descent or shallowest, or steepest ascent or steepest descent. And so people were asking why. And it was a fair question. And I couldn't find it, so I started watching videos, right? I came across that one woman's video, but it's still, she didn't really answer that question. And then I found this video of this math professor, and I'm not going to show it to you, but it's the funniest thing about the video is the math professor, if you can imagine, like, the quintessential professor with, like a tweed jacket with elbow patches and a pipe standing next to a fireplace, right? That was this guy talking about why the gradient gives you the steepest descent. And it was the fun, I'm like, I couldn't believe what I was watching, that it really was this guy, like, in his little fireside chat room talking about, in his tweed jacket, talking about the gradient. But anyway, but then he would switch to graphics, and he actually had, you know, like a little thing that he wrote on and explained it, and I was like, oh, that makes total sense. So anyway, but no, I won't show you the video. But I might pull up the other woman's video, because I really do like her gradient video. It's cute with the skier. It is Fun Friday, right? So I gotta find out that woman's name. All right, so first we're going to do some simple applications, and then we're going to get into our heat seeking, which is a little bit harder, but it's not crazy. And then the rest are all easy.
You would assume that'd be harder because, you know, like, it's a complex topic. I mean, it sounds complex.
It's really not. We don't give you a real hard thing. Yeah, it's pretty simple. Okay. All right. The temperature in degrees Celsius on the surface of a metal plate is given by that temperature function. In what direction from the point 2, -3 does the temperature increase the most rapidly, and what is the rate of increase? Oh, if only we had something that told us when the rate was the biggest, right? Okay, so what are we going to use for this? We're going to use the gradient, right? Okay, so take a minute. Find the gradient of this function, plug in your point. That will give you the value of the gradient at that point. The direction of the gradient at that point is the direction of maximum increase of temperature, and then the magnitude of that vector will give you the actual rate of increase. All right, so our gradient vector was -8x, -2y. When you plug in your point, you get the vector -16,6. I did not find the actual angle. If we wanted the angle, we would do the arctan of 6 over -16, right? So, but I didn't ask for it. The direction vector is fine. So this is your direction of maximum increase. So we're going that way, like second quadrant. Okay. Then the actual amount of maximum increase is the magnitude of that vector, which I got √292, or around 17.09. And I went ahead and put in units, degrees Celsius per centimeter. It's the rate of change of your temperature as you move in that direction on the metal plate. Does that make sense? Not bad? Okay, good. So, next one. The temperature in degrees, this is the only one that's a little tricky. The rest of them are all easy. Okay, I'm going to walk you through it. We'll take it slow. Okay, the temperature in degrees Celsius on the surface of a metal plate is this the same function as the last one? Yeah, 20 minus 4 squared minus y squared. If a heat-seeking particle is located at 2, -3, find the path of the particle. So what happens is when you have a heat-seeking particle, it is always going to follow the path of the gradient, essentially. Like, it's always going to follow where the highest heat source is, right? So it's going to be looking for where the highest rate of change of temperature is going on, right? And it will follow that path wherever it happens to lead it, right? So the trick here is not finding the gradient or anything like that. The path of the particle is typically written in a simple, like, y equals some function of x kind of a function. So we could write the path parametrically as an r of t, which is actually how we're going to start, but then we're going to switch and just do it as a simple y equals some function of x. We could go back once we get it and redefine it parametrically if we want to, but we don't have to. So anyway, so here, let me just talk about this for a minute. So we're going to let r of t, which is an x and a y, parametrically defined function, define the path of the particle. We don't know what that is. We know the gradient, but guys, the gradient isn't the path. The gradient just gives you the direction of steepest rate of change of temperature, but think of it as like degrees Celsius per centimeter. It's not the path the particle is traveling. It doesn't give you an equation of a path. It gives you this like equation of steepest descent. So anyway, so we have this path. All right, so the derivative of the path, the vector tangent to each point on the path would be r prime, dx dt, dy dt. No, but it is going to be a blast from the past. Okay? Today we're going to use a topic that we used last year and we have not used yet this year. Okay. All right. So I'm just going to do a quick off to the side reminder. Okay. dy dx is equal to dy dt over dx dt. We learned this last year. We even used this a little bit when we were doing our polar parametric unit, but we know this year too. So dy dx equals dy dt over dx dt, right? Now, what do we want dx dt and dy dt to equal? We want them to equal the gradient. So we want the rate of change of the path to follow the gradient. So here's the thing. If r prime equals the gradient, that means dx dt equals negative 8x and dy dt equals negative 2y. So we are going to kind of use that information to write dy dx. So dy dx is going to equal our negative 2y over our negative 8x. We want every point on the path to have its, like, to follow that gradient. All right, so we have this equation. I'm just rewriting it bigger. We have dy dx equals y over 4x. What can I do with this equation?
Oh, no, it implicit differentiation.
Yes! Yes! Did you hear that? She said, we can separate the variables and solve it as a differential equation. Right? Get all the x's on one side, get all the y's on the other side, and integrate both sides. It is a thing. Okay. So I'm just going to show you the setup. So when we separate the differential equation, we get 1 over y dy equals 1 over 4x dx. I want you to take a minute, integrate both sides, and see what happens. Okay, so the antiderivative of 1 over y is natural log absolute y. the antiderivative of 1 over 4x, think of it as 1/4 times 1 over x, so it's 1/4 ln absolute x plus c. To solve for y, we want to exponentiate this side. So people were asking me, how do I do that, right? E to the 1/4 ln absolute x plus c. So the 1/4, yeah, c is a constant, and remember e to the c is a constant, so you could think of this as e to this times e to that. And so what I was going to say is, if you want to simplify this e and this ln, the fourth has to become an exponent up here, so that they're next to each other, right? And then you could have absolute value of x to the 1/4 times some unknown constant. Because remember, this is this times this. Yeah, okay. Alright, so anyway, wow, I did a whole lot of, took a bunch of liberties. Let's see. I don't have space. So this, put the 1/4 up, and you get absolute y equals some unknown constant times absolute x to the 1/4. So I don't know how I dropped the absolute. I probably shouldn't. I don't know. Well, technically there can only be one solution to a differential equation. And so what we used to do to drop the 1 around the y is we would just say that our constant, since our constant can only be one constant, it can't be a plus or minus, that you could drop the absolute around the y. And then, I don't know if you guys remember, I used to make you guys change your constant name. But the thing that bothers me is dropping the absolute value around the x. I still feel like the absolute value around the x needs to be there. But, okay, this is where I need more space. I'm just going to kill this and extend page and go down here. All right, so let's do this slowly and just ignore the typing. Okay. All right, so we're just going to go from here. So we have ln absolute y equals 1/4 ln absolute x plus c. All right, so if we exponentiate both sides, we get absolute y equals e to the 1/4 ln absolute x plus c. That whole thing's an exponent. So this, when you have a number in front of an ln, it can become an exponent, like that. And then this could be times e to the c. Okay. So then absolute y equals some unknown constant, and then e to the ln of stuff is the stuff, because these are inverse functions. Does that ring a bell?
Oh, yeah.
So they kind of cancel each other out. They really don't, but they kind of do. So anyway, so e to the ln of x is x, ln of e to the x is x. So e to the ln cancel, and you're left with that. So now, technically, you can drop the unknown, the absolute value around the y, because it's a differential equation. There can only be one solution. You can't have a plus or minus. It wouldn't even be a function then. So we can drop the absolute value around the y and just say it's some unknown constant. We don't know if it's positive or negative, and then solve for it. So how do we solve for it? We got to plug in a point that we know is on the curve. All right, what is the point that's on the curve? 2, -3, right? So we plug in the point, -3 equals m absolute 2 to the 1/4. So m equals -3 over the 4th root of 2. All right, so my final function is y equals -3 over the 4th root of 2 times absolute value of x to the 1/4. So that's what I get. Honestly, I don't know why I dropped the absolute value. I don't think I should have. I don't know. But that's what I get. because the solution to a differential equation has to be a function, and there can only be one solution. So when you drop an absolute value, just, if I have like absolute y equals 5, that means y equals plus or minus 5, right? So when you drop an absolute value, you can do it by putting a plus or minus to the other side, but you can't have plus or minus here because you can only have one multiplier. So I just changed the constant name and said, I don't know if it's positive A or negative A, I'm just going to call it M and say let that be my constant. I will have to check and see. In all honesty, I just don't know why I dropped the absolute value, so I will have to check on that and see why I dropped it. All right, this right here, that is the path of our particle. So if we graph the path, it actually looks like this. This is a level curve for the temperature plate, where the temperature, you've got temperatures, different temperatures surrounding some heat source. And so your path, if you look at it, this is the path that it follows until it gets to the highest heat source, right? And then it stops, which might be why we have an absolute x, because we don't have one, because if we have one, we can have negative x values, and we wanted to stop here. So maybe that's to force it to stop. I don't know. Anyway. Okay, so this is going to take us into the next slide. But before I go to the next slide, just talk to me about the math. Yes, Amal.
I have a question. So I understand why you switched from A to M, but why did you switch from C to A?
Oh, because e to the c, this is e to the c, and I just wanted to give it a one-letter name and not call it e to the c anymore. In all honesty, most people aren't that picky about like changing your unknown constant. It's just it's my thing. I watched a professor last year at the AP conference just sit there and write C, 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 even though she was doing stuff to it every single time. Okay, C plus 5 is C, and 2 times C is C, and now we're going to take the square root and we get C. And she just kept writing it as C. And it drove me crazy, but, she just did it, so. No. So, anyway. All right. So, one last note. If f is differentiable at the initial point, and the gradient at that initial point is not 0, then the gradient is normal to the level curve through x sub 0, y sub 0. So what ends up happening is this maximum, like if this is your level curve, so I don't know what these actual temperatures are, but this is some this is a heat source, and you have a heat-seeking particle, and so this is where like the temperature is, I'm just going to make a guess, like let's say the temperature goes by 100 degrees, so 100 and then 200 and 300 and so forth, or actually it'd probably be higher here and lower here, so 500, 400, 300, 200, 100, something like that, right? So wherever you've got all these level curves surrounding this source, the path of steepest ascent, the greatest, how do I say this? The path where the rate has the maximum increase is normal to those level curves, which kind of makes sense, because if I follow on the level curve, I'm not increasing at all. I'm not even changing. I'm just staying at the same z value, right? So the one that would be the steepest, the most contradictory or highest increase, would be the one that's perpendicular to that level curve. So anyway, so your heat-seeking particle will always, and the gradient will always follow a path that is perpendicular to your level curves. I don't know if you don't need to draw that. Do you need a minute? Oh, you guys draw. It's okay if you do. I'm pausing the tape. They follow the buttons. All right. Okay, easy one. Find a vector normal to the level curve at point P if f of xy equals x times y. Your level curve, the c is the constant that for that level curve, right? So where your level curve is -3, and you're at the point -1, 3. So find a vector normal to that level curve at point P, which is -1, 3. So see if you can find that. It shouldn't take long. I'm going to pause this.
Two variables. Let's take a point down here. Let's take a point x naught, y naught, and plot that point on our surface. Okay? Now, it is a natural question to ask, in which direction should we go so that the rate of change along this curve is going to be the greatest or the least? Said another way, what are the directions of maximum descent and ascent? Okay. Well, we know that the direction of maximum ascent is going to be in the direction of the gradient. In other words, when u and the gradient are in the same direction. That's same, not same. The direction of maximum descent is in the direction of minus the gradient. But let's see what that looks like in this picture. Okay, one thing that I have not told you, it's a property of the gradient vector that's extremely important, but due to budgetary constraints, we did not have time to prove this. We've actually done most of the work, but at any rate, if we slice through a surface with a plane where z is a constant, then what do we get? Well, in this case, it looks like we get a circle or an ellipse, depending on what the equation of that surface is. And it is a fact that, so this is called a level curve, and it is a fact, and an important fact, that at any point the gradient vector is always perpendicular to level curves. So the gradient vector is perpendicular to level curves. What does that mean? Well, remember, the gradient vector is a two-dimensional vector, not a three-dimensional vector. So it means that once we have this curve, there's kind of a tangent line to that curve, and perpendicular to that, in one of those two directions will be the gradient vector. Now, I drew it so it kind of looks like it's pointing upwards, but it's down here. We could draw it in the xy plane. So let's think about this in terms of doing some skiing. Now, I have a family friend, Katya. She is in college now, but I have discussed mathematics with Katya since she was in 8th grade, and she's a very bright young woman. Let's see Katya. There she is. So I'll give her some ski gear. She has lived all over the world, and she has, in particular, skied the Matterhorn. Let's make her ski vectors. Why not? Give her some poles.
I think it's pretty good.
Now, Katya has skied the Matterhorn, which is in the Alps. It's a mountain between Switzerland and Italy, and it looks a little bit like that. So let's assume that Katya is at this point on the surface of the Matterhorn. Now, because I care about her safety and well-being, when Katya decides to ski downhill, I would of course hope that she does what most reasonably cautious skiers would do, and that is zigzag down the hill or down the mountain. However, let's assume that for a moment Katya wants to go down that hill and experience the maximum rate of descent. So let's say she wants to go in the direction that will give her the maximum rate of descent. Well, we know that that is minus the direction of the gradient. Now, in this case, because of what we said about gradients being perpendicular to level curves, the gradient is actually going to be this vector pointing inward, Why is that? Because when we take this vector and plot the corresponding points along the surface, we get a curve. And so it's that curve that has the maximum rate of change in that direction. What if we go, so this in fact is the gradient vector. What if we go in this direction minus the gradient vector? Well, what does that mean? It means we take these points and we plot them on the surface. And if Katya skis this way, she will enjoy the maximum rate of descent down the Matterhorn. Now, there's something slightly subtle here. Because she's going up or down the hill, down probably, it feels like maybe the vector should point down like this or something like that. But remember, the gradients, it doesn't, because if she went in that direction, she would go into the ground. If she went in a direction like this, she would fly off into space, which we certainly don't want to happen to Katya. But the vector that we're interested in, the gradient, is a two-dimensional vector. So all it means is that it creates a curve along the surface, and it's that curve that will have the maximum or minimum rate of change. Now, this property of the gradient is extremely important. If you've ever seen water trickling down a mountainside from a stream, perhaps, it always takes the path of maximum descent. That means that at any given point, the water will travel in the direction of the gradient. And many of the fundamental applications of the gradient depend on those properties. So I hope that I have shown you in this second video, at least to some extent, that the directional derivative really does contribute to some of the success that the gradient enjoys. I don't.
Okay. So now you all is clear. Okay. So for our problem, if we need to find a vector normal to a level curve at a point, all you're finding is the gradient and plugging in the point. That's all you're doing. All right? It gives you a vector normal to a level curve at a point. We didn't put it on the video. It's there now, though. I sketched a quick sketch of the level curves for this function, found where the point was we were interested in, and drew a quick sketch of the direction of the gradient, and it is perpendicular to the level curve. All right, let's try another one. Use the gradient to find a unit vector normal to the graph of 3x squared minus 2y squared equals 1 at the point 1, 1. So take a minute, find the gradient, find the point, and then turn it into, the only difference here is that it asks for a unit vector. You may analyze, yes. If anyone ever asks me to prove why a vector of the gradient is normal to the level curves, I am always going to answer with that answer. Due to budgetary constraints, I cannot prove that.
She said Katya's in college now, but then she said she's in 8th grade.
No, she said she'd been talking with her about math since she was in 8th grade. So Katya is some girl. Imagine a skier. Yeah. That's true. All right. Did you find the appropriate gradient vector? Was your gradient 6x and negative 4y?
Yeah.
Did you plug in the point?
Yeah.
Did you turn it into a unit vector?
Yeah.
Then you can go get one. All right. So you plug in your point, and then you just have to turn it into a unit vector. It's the only difference. Whoa. Is that okay? All right, let's do another one. Oh, wait, that's it. Oh, I thought there was one more. I was sure I had one more example. Okay, due to budgetary constraints, we will have to end the lesson early. No, actually, before I release you and let you go, no, I'm not letting you go at all, but I mean like stop the lesson. Oh my goodness. Oh, what a day. Those of you watching the recording, it's Friday, 4th period. That's why this is like this. Okay. Let's see. So I just want to make sure that I'm not giving you any problems that you can't do. All right, so, ooh, look at that beautiful graph with level curves. All right. Oh wait, hang on, let me turn the key off so you don't get to see the answers. Okay. All right, so level curves for barometric pressure in millibars are shown for 6 a.m. on a day in November. Hey, look, and it's like around us too. It's like they knew that we were doing this. Okay. A deep low with pressure 972 millibars is moving over northeast Iowa. The distance along the red line from Kearney, Nebraska to Sioux City, Iowa is 300 kilometers. Estimate the value of the directional derivative, of the pressure function at Kearney, that's here, in the direction of Sioux City. So you have to, that's interesting, you have to approximate the value of the directional derivative. Guys, it's really your rate of change in this direction. So how do you figure out the rate of change? Well, it'd be the change in barometric pressure, which you'd have to do by kind of following these level curves around to get whatever the amounts are for starting and ending, over the change in that distance, which is 300 kilometers. And then see if you can figure out the units. All right. So that's kind of an interesting one. Let's see. Rate of change. So here's your potential function. Rate of change in this direction, directional derivative. In what direction does it change most rapidly? What is the maximum rate of change? All right, I'm going to just check and see. Do they give it at an angle? Nope, they have you give it as a vector. So when they ask you for the direction, of maximum change, they're having you write it just as a vector. They don't make you find an angle. All right. Climbing a hill, if you stand at this point, let's see, if you walk due south, are you going to start to ascend or descend? That's kind of interesting. At what rate? So you're finding a directional derivative, straight south. So you got to think about what angle to use. Northwest, same thing. These are all just directional derivatives. In which direction is the slope largest? We're just talking gradient. All right, gradient vector, use it to find the tangent vector to the level curve. Oh, that's kind of interesting. Okay. So remember that the gradient is always perpendicular to the tangent, right? So that should be kind of a hint for you to figure out the tangent line. All right. Same kind of a thing. Your homework's really easy. And then find the maximum rate of change to the point. Again, you're just doing gradient. So let's see. Oh, and the maximum rate of change, that would be the magnitude, and the direction would be the direction. So you could totally do your homework. There's no heat-seeking particles. Everything's very normal. So I think we're good.